will receive the maximum power from the circuit if the load resistance equals to 70 equivalent of the circuit. Okay? So maximum power you can get is how much then? If this is R, so that will be half of your V total, or 70 times 1, right? So that's 1/4. RL. So it will be VTH over 4 RL. That's the maximum you can get. Okay? Now, that's all for this week. Okay? You will have a take-home exam next week. So I'll email you, and please email me the answer within the time frame I said. Okay? That's all for today. For you to solve, right? So we will not carry out. So that's how we solve the mesh analysis when with a current source in the middle. Now, if we replace this guy with a voltage source, we don't need to do this because do we need to do this? Let me ask you: if I replace the replace the 3 amp current source with a voltage source, do we need to do this big loop again, or we can use the old way? Okay. So the whole issue of we have to go through the big loop is because if we assuming IA and IB is known, we have no way to write the KVL of this guy. But it's not 2. The voltage drop of this guy it's not 2 if it is a voltage source. So for example, if it is if we have the same situation, but I replace this guy with a 3 volt or VS. It says this is a VS. So we can still write KVL. So that will be 18 for the KVL for the first loop. So if this is a pure VS, again we can write the KVL of this loop, which is 18 equal to 3IA. If this is drop, so then plus VS, then plus this one drop, so that's 2IA. Again for that loop, So we have a race. So BS will equal to 9IB. And then we saw a drop, so it's minus 15. Saw a raise, it's minus 15. Then plus 6IB. Okay? So assuming VS is known, so we have unknown is IA and IB, then you can solve. So it's pretty straightforward, just like a resistor. The only thing different is when this is a current source, then you have to use the big loop to solve the problem. Okay? Okay, so that's all we have for mesh. Now, so we have two analysis. One is nodal analysis, so which is based on KCL, and we have mesh, which is based on KVL. So for this one, you need to find out n number of nodes, then you have n equations. So for mesh, you have m number of mesh, then you have m number of equations. So for you to simplify your work, you need to find out if you're not sure which one to use. Then if if node is less than mesh, you use nodal analysis. It's nodal. If the number of mesh is less than node, so use mesh analysis. So some examples where you should use node. So where you, for example, if you have this, something like this. If you have many mesh, then it's much easier and messy. It's a lot. You have to have 1, 2, 3, 4, maybe 4 mesh for this one. So it's much easier for you just to write node for you have just this one and this one. So it's much easier. So now another example is you have a lot of nodes, which is something like this, something like this. So you have one mesh, but you have 1, 2, 3, 4, 5, or maybe 6 nodes. So it's much easier to use mesh now. So again, I forget to mention. Okay, there are ideal voltage source like this, and ideal current source like what we have seen before. So, but they are, it's called independent voltage source because the value doesn't change. It's independent. However, there's something to model our complex real world. So sometimes we need something called a dependent source. Like for example, this guy is a dependent current source, and its current is depending on the voltage of another guy. So if this labels, this kind of label means if the voltage drop of this guy is delta V, V delta, then the current of this guy is 6 milli times the voltage. So basically the current of this one is depending on the voltage of this one. Of course, this is called voltage controlled current source, right? Because it's effectively a current source, but it's voltage controlled by this one. So again, we can abbreviate as VCCS. So there are other types of, okay, for this current source, it can be current controlled as well. Current controlled, some other current. So we call it CCCS. And then we have voltage controlled voltage source. So, which is VCVS, and current controlled voltage source. So that's CCVS. Okay, there are four type of dependent source: VCCS, CCCS, VCVS, CCVS. Okay, so this is VCCS. So there's nothing different. Either a ideal voltage source or independent voltage source, or it's a dependent current source. We still have to do either nodal analysis or mesh analysis, if depending on which one is easier. So for this one, so let's see how many mesh do you have. Okay, you have one mesh. But this is not a loop. This is not a loop, so it's not a mesh. So this is another loop, So you have 3 mesh. So let's see how many nodes you have. You have this guy, 1 node, and 2 node, 3 node, and you have this one, 4 node. Okay. So. But however, since this node is very easy, is known already by this one, so maybe effectively you can think of 3 nodes. So it's same complexity. So you have effectively 3 node and effectively 3 loop. So depending on your personal choice, you can find out which one to use. So let's do using a nodal first. So we label this as 1. Let's call this VS. This is node 1 and node 2, and this is ground. So so for nodal, we then write a KCL, right? So we need to find out what's the current of this one and what's the current of this one. So the current of that one which is let's say R1, R2, R3, R4. So current of flowing through R1, which is this one minus this one, right? So IR1 will be 6. So it will be Vs minus V1 over 1K, right? Very straightforward. So IR2 will be this one, 5K of voltage drop across it, so V1 minus 1. Very straightforward, right? Now, so IR3, which will be 2K of we know 2 minus 1, right? And IR4 will be again same, just only this one is different of V2 minus 0. Okay? So then we found the KCL at this node. So that which means IR1 will equal to this current flowing through here will equal to IR2, right? So that means, which means this one equals this one. So for this one, okay, so KCL at this node. So so there's nothing flowing out, so that will be 0 or equal to everything flow out. So that will be IR3 plus IR4 plus this guy. That's 6E minus 3 V delta. Okay? So that means, let's solve the first one first. So that means 5Vs minus 5V1 will equal to V1. See, it's kind of independent, so it's easier to solve V1 directly. So V1 will be so 6V1 will equal to 5Vs. So V1 will equal to 6 of 5Vs, so which is 50 volt. So this node is 50 volt. So it's very straightforward, right? And you have a 1K and a 5K, it's a multi-divided, so it's 50 volt. Very straightforward. Now, so then we know what's V delta? V delta is V1, right? So that's times 50 volt. So that means um, um, that means V2 over 2K plus V2 over 0.5K will equal to minus 50 times 6 E minus 3 will be 0.3, right? It will be 300 E minus 3 will be 0.3. So, which means everything multiplied by 2K, then 5 V2 will be minus 0.3 times 2000. So, which is 600. So 5 V2 equal to 600. V2 will be 120. Minus. Okay? So this node is minus 120 volt. So how much is I1? So I1 then is 20 over 2K. 120 over 2K, that's 60 minus I1 is minus 6 milliamp. Minus 60 milliamp. IO will be 120 over 500, so it will be 240, minus 240 milliamp. And then, so it also requires you to solve for I2. How much is I2? So then we need to find a KCL equation for this node, right? So we know the current of this guy has to equal to the current of this guy, right? There is it can be anything out of the current source, but the terminal, the current flowing out of the positive terminal must equal to the current flowing out of the flowing into the negative terminal, right? And this current flowing out of the terminal will all the way down become this current. This causes Ix and Iy. So that means this I at this node. Even if it's hooked up by wire, we still can do a analysis of this particular subnode. We'll call it subnode. Okay, so we can still do KCL at this node. So let's say so what you have is you still have I2 will equal to Ix. So the current flowing in will be Ix plus I2. Current flowing out will be Iy. Okay. So because you know Ix has to equal to Iy, because the current flowing to the negative side of the voltage source has to be equal to the current flowing out of the positive side, right? There's no way you can mysteriously add some current or drop some current. So Ix equal to Iy means I2 must be 0. Okay? So that's the problem we have solved. Okay? You kind of remember what we said for the ideal voltage source before, ideal elements before. So remember what we said. If something like this, right? As long as this current equal to this current, and the voltage can be 0. it's a short, right? But it can still have current. This is physically valid. And as shown here, although this is hooked up by a wire, you can still do a subnode, and you use KCL for this subnode. Then you still get the correct solution. So that's so far what we have now for circuit with dependent source. Now let's move on to principle of superposition. So if you have a 2 voltage source in series, so which can be combined like V1 plus V2. Similarly, if you have 2 current in parallel, you can merge it as 2 in I1 plus I2. So, so the superposition is you can determine the contribution due to one independent source and then repeat, and then you sum them up. So this is an example where you can use superposition to find out circuit parameters. So if you try to find out V0, which is a voltage across the 4 ohm resistor, you have 3 sources, right? 24, 4 amp, 4 volt, and you can try to find the contribution of each one on the 4 ohm, then you add them together. Okay? So, before we can do that, so we need to find out a way to get rid of the voltage source from the existing circuit. So, so how do we get rid of the? Let's say we have 3 voltage sources. We're trying to solve, find out how much each one is contributing to the output. So then we need to get rid of other voltage source or current source. So again, this is shown as open circuit and short circuit. Okay, if you want to turn off an independent voltage source, it means you short that voltage source by wire. Okay, so that means the voltage is 0 now. You short them by wire. Now, if it's ideal current source, what you do is you make it open, doesn't contribute any current, because it's open current doesn't. Open circuit doesn't contribute current. Same as voltage source. If it's a short wire, then it doesn't contribute to serious voltage drop. So now let's see how we can get rid of each case. Get rid of the voltage source one by one. Okay. Now let's see. We're interested in how much the 24 will contribute to VO. So we draw another circuit. So you have 24 volt. Then we have the 2 ohm. So for this guy, we want to get rid of this one, the influence of this one, right? So we left it open. And 4 volt is we also want to get rid of. So that's a short. So which means you have this one. And so this is 2 ohm, this is 4 ohm. Okay, so so it's very simple voltage divider, right? You have 2 and 4. So your VO, let's say VO1. So VO1 will be total is 6 ohm and drop out of 4 ohm over your 24. So which is 16 volt. Okay. for the first case. A second case is where you left the this one and you short the voltage source. So what you have is you have VO. This is 2O. This is 4O. This is 4M. So contribution of so basically you have a current. You have two ways to go. One is going this way, and the other way is going this way, right? Of the 4N current. And notice your VO will be negative because your current is flowing the other direction of your sign. So so your 4N will be split two-way, and if this is I, because of the same, because it has the same voltage, this side has to be 2I, right? Because it's only 2 ohm. So 4 ohm times I will be equal to 2 ohm times 2I. So your 4M is total of 3I. So your I will be 4M over 3. Okay? So your contribution of this one to the output, so VO2 will be minus 4M times divided by 3, okay? 4M divided by 3 times 4. So it's minus 16 over 3. That's VO2. Okay? Last one. We saw how many contribution 4 will contribute to the output. So that will be 2O short and a 4 volt and a VO like this. Okay? So again, it will be a voltage divider, but notice that 2O and 4 is a voltage divider. But VO3 will be a voltage divider, which is 6 out of 4. 4 out of 6 times, okay, notice this is a negative one, so negative minus 4. So it will be minus 16 over 6. So it will be 3 of minus 8. Okay, so what you have is you sum them together, so your VO will be VO1 plus VO2 plus VO3, which is 16 minus 3, 16 over 3, 8 over 3, so which is 16 minus 3 of 24, which means 16 minus 8 equals to 8. So VO will be 8 volt eventually. And this guy contributes to 16 volt out of this one, and this two contribute a negative, which means the other direction. Okay. So this is much easier to solve. Looks like much easier to solve. Also, you can use the traditional KCL, KVL. Okay. You have 1 node, 2, 3, 4. 4 node, you have 2 loop. So maybe mesh is easier. Mesh method, you have only 2 equations. So you can solve for the So sometimes we want to break the circuit into modules, so or sub-circuits. So we can analyze them hierarchically. So we can type. So maybe when the circuit is so complex, we can break them into blocks, and we analyze them. We analyze them block by block. Then we hook up the top, hook up the whole the whole system. So it's like divide and conquer method. So, but then we need to find a way we can. So if we solve individually, how do we hook them up together? So we need to have the concept of equivalent circuit. So basically, if you have a sub module or sub circuit, or just maybe for other purposes you have a whole circuit, then you can. It's a bunch of network of R's, capacitor, inductors, dependent voltage source, independent voltage source, current source, etc. So you have do the analysis of the whole network, and you find out what's the current going out, going in, IA, and what's voltage. So basically, then from the user point of view, you don't care what's the detail of the whole thing. The outside world just need to know, given this much of voltage, what's your current will look like? Okay. So I just need a function of output voltage and the current. So. So there are two kind of equivalent circuit. So we'll talk them one by one. So one is a thermally equivalent circuit. Okay. If you have a network, then we're trying to replace it with a voltage source and a resistor. That's the whole concept. Okay. So how to make the IV curve looks the same? If the IV curve inside and the voltage output is same for both one, then we think this one did a good job representing the whole complex network. Okay, so we simplify a bunch of network of elements to two sources, voltage source and a resistor. Okay, so but to do these are the variables we're trying to solve. We'll need to find out what's VTH and what's the RTH. So that is done by equating the make sure they're representing the same IV curve to outside world. Okay, so for outside world, we can do a bunch of tests. Okay, we can leave this open, so we can measure the voltage, and then we can short the wire. We can short the output. We can measure the that is called open circuit voltage. Then we can short the wire, which is the short circuit current, etc. etc. So that open circuit voltage and short circuit current has to be equal in both cases. So this one has to represent the same open voltage current and short circuit current, open circuit voltage and short circuit current. So let's see. So if this one is an open circuit, so it will present a VTH to the outside world. So if this one is a short circuit, so what's the current flowing out? That will be VTH over RTH, right? So if you somehow figured out what's the short circuit current for your complex network, this one just needs to be equal to that one, IEQ. So that then you can find out, because you already find out VTH because we already find out VTH is V open circuit, right? But then you can find out RTH is your I equivalent is your open circuit divided by your short circuit current. Okay, so that's very simple. Now, looks we're on the right track. Let's do an exercise. Okay. So now we have a 3 resistor, 1 voltage source, 1 current source network. So we're trying to simplify to a equivalent, summary equivalent circuit, which is only a voltage source and a resistor. So first step, find out the open voltage, open circuit voltage. So that means when this one's open, what's the voltage at these 2 terminals? So again, we can easily use superposition. Okay, if we use superposition, so from this one, this is open circuit, right? When we superposition, let's say, so you'll have an equivalent circuit of this one, and a 12 ohm, and a 2 ohm, and a 6 ohm, something like this. Okay. Okay, notice there's no use for the 2 ohm because it has no current. Then this voltage of this node is equal to this voltage because there's no current for this resistor. It's an open one. So that means we can just the V out one is basically this minus this. So that means is a voltage divider 12 plus 6 over 6 times your Vs, which is 12 ohm. So it's 18 of 6 multiplied by 12, right? Which is, if you're trying to simplify, 3 over 12 is 4, right? Now, for the other case, without the voltage source, you have 8 amp, and this is short. It's node A and node B. So first you have this drop, then you need to find out what's the current of this way. So it's 12 and this is 6. Again, this will get 3 of 8 amp, 1/3 of your 8 amp. This will get 2/3 of your 8 amp. So VA minus VB will be 8 times 2 ohm plus 2/3 of 8 amp times 6 ohm, right? So that will be 16 plus this is 32. So that will be 48. So your VO2 is 48. So you have total of open circuit will be VO1 plus VO2, which is 52. Okay, I did this open circuit voltage by superposition. You can do it using nodal or other ways. So now then we need to find out what's the short circuit current. Now, if I short here, what's the current? Any idea? So we can use mesh, right? This is I1. So this is I2. So this one we don't need to draw because it's already 8n. That way. So for loop number 1, so 12 will be this current will be 12 ohm times I1 minus the 8m plus this one. So that will be I1 the current going down will be I1 minus I2 plus 6 of I1 minus I2. Okay, so that's KVL for the first loop. KVL for the other loop, that will be for drop of this resistor will be 2 ohm times I2 minus 8. Okay, again there's a minus sign. Plus let's see how or equal to how much this minus this, right? So which will be 6 ohm of I1 minus I2. Okay, that's the two equation. So rearrange it. So 12 will be equal to 18 I1 minus 96 minus 6 I2. So and then this one 2 I2 minus 16 will be 6 I1 minus 6 I2. So so equal to 6 I1 equal to this one will be 8 I2 minus 16. So minus 16 will be 6 I1 minus 8 I2. Okay? So we put this back on this side, so that will be 108. It will be 18 I1 minus 6 I2. So this guy multiplied by 3 and minus, so 106 plus 16 times 3 will equal to minus 6 minus minus 8 times 3 I2. So 108 plus 48 will be equal to 24 minus 6 I2. So I2 will be 18 of 156. So that will be 7. No. 156 over 18 is how much? Uh, 8.6. Okay. Okay, so I2 will be 8.6, and then you can find out I1. So anyway, I2 is what you need, right? I2 is 8.6, and you have the open one, open voltage of something. So you have the equivalent one of RTH of something over 8.6. Okay. So we need a hurry. So same situation happens if we have a northern equivalent one. So northern equivalent one is basically very similar. Only replace replace the ideal voltage source with the ideal current source. It's in parallel with the resistor. Okay. So same situation. How do you so again, same thing. You find out open circuit voltage and short circuit current. So then, for this one, the open voltage, so open voltage will be equal to Im times Rm, and short circuit current will be equal to Im. So you find out this one, then your Rm will be V open over I short. Okay, so this is this applies in both northern and Thevenin. Okay, so basically they are not independent. They are trying to describe the same circuit, so they are correlated. They are not independent. Okay. So before we finish this week, let's talk about maximum power transfer. So if you have a complex circuit, and then we already find out the northern or Thevenin equivalent, so we know the VTH, RTH. So we're trying to find out what's the best loading you can get to take the maximum amount of power out of this circuit. So again, power is I squared times R, and this is simply a voltage divider, right? So the I will be VTH over total resistor. So so this is the equation, and then you try to differentiate versus RL, right? If you wanted to get some maximum, you differentiate. So which turned out to be if you do the derivation, find out if the loading resistance is equal to this guy, then you get the maximum power out. So resistive network and resistive net